So, every time you ask a massive AI to, like, write you a line of code or maybe draft an email.
Yeah, or even just summarize a document.
Right, exactly. Behind the scenes, there's this multi-million-dollar supercomputer just agonizing over it.
Literally agonizing.
Yeah, like one single syllable at a time.
Uh-huh.
It's honestly a bit like using a Formula One race car to, deliver the morning paper house by house.
That is a great way to put it, actually.
Because these large language models, I mean, they're brilliant, right? They can pass medical boards, they handle dense legal briefs, but watching them physically type out an answer on your screen...
It highlights a massive bottleneck.
Exactly. It can feel painfully slow for you sitting there at the keyboard, and that's because they generate text auto-regressively.
Right, meaning they compute the first word, feed that word back into the system, compute the second word, feed that back in, and so on.
It's incredibly computationally heavy.
It is.
Yeah.
And, that latency goes way beyond just your personal annoyance at a blinking cursor.
Right, there's a real cost.
A huge cost.
Yeah.
As these models scale up into, like, hundreds of billions of parameters, their inference cost. I mean, the raw electricity and silicon required to generate answers token by token, it's dominating the budgets of the companies deploying them.
So finding a way to fix that is huge.
Arguably the single most pressing challenge in generative AI research right now.
Yeah.
How do we reduce that latency without degrading the actual quality,
So for this deep dive, we are examining a cutting-edge generative AI research paper. It's called PARSE, Parallel Prefix Verification for Speculative Generation.
It's a bit of a mouthful.
Yeah, definitely. But it introduces a framework designed to make AI dramatically faster. And to understand how it works, I kind of want to frame the core problem differently.
Okay, go for it.
So imagine you have a friend who is an absolute genius.
Correct.
Like flawless understanding of quantum physics, history, whatever you need. But they type with just 2 index fingers. Right. If you need a 10-page report from them, you are waiting all week. But what if you hired a highly caffeinated, incredibly fast-typing assistant?
I like where this is going.
The assistant drafts the response at lightning speed, and your brilliant friend just reads over their shoulder. If the assistant gets it right, the genius friend just nods and lets it go.
Yeah.
But if the assistant messes up, the genius stops them, crosses out the error, and dictates the correction.
You've essentially just described the exact mechanics of what the industry calls speculative generation.
Oh, perfect.
Yeah, it relies on pairing a lightweight, fast draft model, your assistant, that proposes words or tokens with a massive, highly capable target model that acts as the verifier, the genius friend.
So the big model doesn't have to do all the heavy lifting of typing.
Exactly. Because the fundamental premise here is that verifying text, reading it to see if it makes sense, is computationally much cheaper and faster for a massive neural network than generating that same text from scratch.
That makes a lot of sense.
Yeah, it allows the system to process large chunks of text in parallel, rather than being trapped in that one word at a time loop.
But the way we've been doing this reading over the shoulder technique hasn't exactly lived up to the hype, has it?
Well,
no, not quite.
Because there's a fatal flaw in how the genius friend is currently grading the assistant's work.
Right. So the conventional approach is called classical speculative decoding.
Okay.
In this setup, the draft model spits out a sequence of tokens, and the massive target model verifies them strictly at the token level.
Wait, so literally word by word?
Literally word by word. It checks the draft against the exact statistical probability of what it would have generated itself.
Wow, okay.
It uses a statistical method called rejection sampling, which is mathematically lossless, meaning the final output you see on your screen is guaranteed to perfectly match what the big model would have written if it were working alone.
I mean, a mathematical guarantee of genius-level output sounds ideal.
It does. But if it's checking every single word against its own internal dictionary predictions, that has to create a lot of friction.
A massive amount of friction, yeah.
Yeah.
Because the target model has to agree on the probability of every single token, the acceptance lengths, like the number of drafted words the big model actually approves in one continuous streak, end up being extremely short.
So wait, if the fast assistant writes, the car is fast, right? And the brilliant target model, based on its own internal weights, was heavily favoring the phrase, the car is quick, does the target model reject the entire sentence over a simple synonym?
It does.
Yeah, that is insane.
Even if the semantic meaning is perfectly accurate and totally valid for answering your prompt, Classical token-level speculation will reject the draft if it deviates too far from the specific word choices the big model prefers.
That is like the ultimate micromanaging boss.
Exactly.
Imagine staying up all night writing a flawless, logically sound 5-page report. Your boss reads over your shoulder, sees you use the word fast instead of quick in the opening paragraph.
It just rips the whole thing up.
Yeah, immediately throws the entire report in the shredder and makes you start over from that word. I mean, it totally defeats the purpose of hiring the fast assistant.
Right. Why bother if you are going to throw away perfectly good work over stylistic differences?
Exactly.
And researchers recognize this bottleneck because for most tasks you actually care about, having an AI solve a math equation, write a Python script, summarize a meeting.
Right, the exact wording doesn't matter as much.
Exactly. Correctness is not about matching the target model's exact vocabulary word for word. It is about whether the draft is on a correct solution trajectory.
Is the reasoning sound?
Is the factual context right? A synonym doesn't break a math proof, you know.
So if checking individual words is too granular and creates this whole micromanagement problem, the logical next step would be to have the big model grade larger chunks, right?
You'd think so, yeah.
Like, why not just have it grade whole paragraphs or complete reasoning steps?
Well, that is exactly where the field went next. It's called semantic-level speculation.
Okay, semantic level.
The paper references prior frameworks like spec reason and speculative thinking. Instead of looking at individual tokens, these approaches evaluate a larger semantic span.
Like a full thought.
Right, like a complete intermediate reasoning step in a complex logic problem. The fast draft model proposes an entire thought, and the large target model acts as a judge, evaluating whether that specific logical step is sound before allowing the system to move forward.
Oh, okay. So the synonym problem is gone.
Mostly, yes.
We are no longer throwing away good work over the word quick. We're reusing much larger chunks of the draft model's output.
We are, which definitely increases the theoretical efficiency. But by fixing the token-level problem, these semantic approaches introduced a brand new architectural issue.
Of course they did. What is it?
Strict sequential dependency.
Okay. How does that play out when the model is actually running?
It basically forces the entire system into a stop-and-go loop.
Yeah.
The draft model generates a complete semantic chunk, say paragraph A. Then the entire generation process halts while the massive target model loads paragraph A into its memory and verifies it.
Oh, I see.
Only after paragraph A gets the green light can the draft model start generating paragraph B. Then everything stops again for verification.
So we basically traded the micromanaging boss for a boss who locks their office door.
Pretty much.
The assistant writes a paragraph, slides it under the door, and then has to stand in the hallway doing nothing until the boss finishes reading it.
Yep.
Slides it back with a thumbs up, and only then can the assistant write the next paragraph.
And that serial bottleneck destroys a lot of the speed gains you get from checking larger chunks. You're looking at a fundamental tension in AI inference right now.
Which is?
Well, token-level verification lets the big model verify many words in parallel, one pass through the GPU checks a whole sequence of tokens, but it rejects things so often that you barely make progress.
Right, the micromanaging.
Exactly. But semantic-level verification lets you accept big, meaningful ideas, but you have to check them one at a time sequentially.
Starving your GPU of parallel processing power.
Exactly. You are either checking fast but too granularly, or checking big ideas but too slowly.
Which sets the stage perfectly for the actual breakthrough in this PARSE paper.
Yes, it does.
Because PARSE stands for Parallel Prefix Speculative Engine.
Right.
And we need to understand how it breaks this trade-off, because getting both the big semantic chunks and the fast parallel checking sounds like a contradiction.
It does sound like magic, but it requires a shift in how we utilize the target model's attention mechanism.
Okay, lay it on me.
Instead of generating and checking segment by segment, PARSE allows the fast draft model to run completely uninhibited.
Wait, really?
Yeah, it writes a finished complete candidate answer from start to finish.
The whole thing?
The whole thing. Then, PARSE takes that entire completed draft, hands it to the large target model, and essentially asks it to verify all the possible prefixes.
What do you mean by prefixes?
Meaning every semantic chunk from the beginning up to various stopping points. And it does this simultaneously in a single forward pass.
Okay, doing it simultaneously is the part that sounds impossible. How can a model evaluate paragraph 1 on its own, then evaluate paragraph 1 plus paragraph 2, and then paragraphs 1, 2, and 3, all at the exact same time,
Right.
without the text bleeding together and just confusing the model.
So to understand how, we have to look at how large language models process information through causal masking.
Okay.
Normally, when an LLM reads a sequence of text, each word is only allowed to look back at the words that came before it to build context.
Right, so the word bank looks back at the word river to know it's not a financial institution?
Exactly. If it reads a full draft to the end, the final internal state of the model contains its judgment on the entire text. But during that single read-through, what we call the prefill phase, the model is actually computing a hidden state for every single word along the way. The knowledge about whether the logic is sound up to that specific sentence is already being calculated in the model's memory.
So the knowledge is already sitting there in the GPU, we just haven't been extracting it.
Precisely.
So if the assistant slides the completely finished 5-page report under the door, we just need to give the boss a way to evaluate different stopping points simultaneously.
Yes.
It makes me think of giving the boss a pair of augmented reality glasses.
Okay, AR glasses.
Yeah, when they look at the report, the lenses kind of fracture their vision. In their left eye, they only see page 1. In their right eye, they see pages 1 and 2. They are processing different boundaries of the report at the exact same millisecond.
That visual maps very closely to what PARSE achieves using a custom attention mask combined with duplicated suffixes.
Okay, what's a duplicated suffix?
They take the finished draft and insert a specific hidden prompt suffix that basically asks, is the reasoning up to this point correct?
Oh, I see.
And they put it at multiple different boundaries throughout the text.
Wow.
So after paragraph 1, there's a suffix. After paragraph 2, another suffix.
Like a bunch of checkpoints.
Exactly.
Yeah.
But here's the trick. They alter the attention matrix. They mathematically blindfold these suffixes from one another.
So they can't see each other.
Right. Suffix number 2 is allowed to look back at paragraphs 1 and 2, but the mask strictly prevents it from seeing suffix number 1.
Because if they saw each other, the model would get completely confused by a bunch of repeating questions embedded in the text.
Exactly. By isolating them with the attention mask, the target model processes the entire document in one single forward pass, but outputs multiple independent judgments for each chunk at the exact same time.
That is brilliant.
It is. It identifies the maximal valid prefix. It finds the absolute furthest point in the draft where the logic remains sound.
And keeps it.
Accepts everything up to that exact boundary, and only takes over generation from the precise moment the draft model hallucinated or made a logical error.
So it eliminates the hallway waiting entirely.
Completely.
The assistant dumps the full report on the desk. The boss puts on the glasses, instantly circles the exact sentence on page 4 where the math fell apart, keeps all 3 previous pages, and just fixes the ending.
Yep. And from a hardware perspective, because this is all happening in one forward pass, the verification cost is incredibly low.
Like fractions of what it would be.
Very low.
Yeah.
It maximizes GPU utilization instead of leaving the processor idle while waiting for the next chunk to be drafted.
Wow. Okay, so the mechanics of the attention mask are brilliant. But while I was reading this paper, I found the behavioral discoveries they made just as compelling.
Oh, absolutely. The psychology of it.
Yeah. To make this work, the researchers had to figure out if these large models are actually competent at being judges of someone else's work.
Right, because if they're bad judges, the whole thing falls apart.
And it turns out the psychology of an AI judge operates under some very specific rules.
It does. For PARSE to function, the target model's correct or incorrect judgments have to be ironclad. And through their testing, the researchers made 3 distinct empirical observations. The first one is foundational. Judging is easier than answering.
I think every person who has ever left a restaurant review intuitively understands that.
Exactly.
But what does it actually mean for a neural network?
It means that a large target model can consistently and accurately flag a draft answer as incorrect, even on complex reasoning questions, where the target model itself does not know the correct answer.
Wait, it can spot an error without knowing the real answer?
Yes. The empirical data showed the model's error detection coverage was significantly higher than its baseline answering accuracy.
That is fascinating.
It can recognize that a logical leap in a draft is invalid, or a mathematical operation violates the rules of algebra without possessing the internal knowledge to generate the correct proof from scratch.
I mean, that makes perfect sense. If I'm reading a complex astrophysics paper, I could never write out the formulas for gravitational waves.
Yeah.
But if the author suddenly writes, "And therefore the moon is made of cheese," I don't need a PhD to flag that as a catastrophic logical error.
You really don't.
I can judge the failure without being capable of producing the solution.
And PARSE leans entirely on that asymmetry. As long as the large model is a robust detector of errors, it can safely supervise a much faster, error-prone draft model.
Right.
But that brings us to the second observation, which deals with how you extract that judgment. They found that relying on the model's top word choice is a terrible way to judge correctness.
The paper calls this confidence beats argmax.
Yes.
We should probably translate argmax for anyone who doesn't spend all day reading AI papers. When an AI is trying to decide if a draft is correct or incorrect, how does it normally choose?
So normally when an AI generates a response, it calculates a probability distribution across its entire vocabulary for what the next word should be.
Right.
And it simply selects the word with the highest probability. That process is called taking the argmax.
Okay, so just picking the highest percentage.
Right. So if the model calculates a 51% probability that the draft is correct and a 49% probability that it is incorrect, the argmax is correct. It outputs that word and moves on.
But 51% is just a coin flip.
Exactly.
If I take a multiple choice test and circle C just because it looks slightly better than B, I'm taking the argmax. I don't actually know the answer, I'm just guessing.
And the researchers realized that if you just rely on that argmax guess, the target model misses a huge volume of errors.
Oh, wow.
Yeah, it only catches about 60 to 70% of the mistakes in the drafts.
Well, if the boss is missing a third of the factual errors in the report, the final product is useless. You lose the guarantee of quality.
Exactly. So they stopped looking at just the top word and started looking at the model's internal uncertainty.
How do they do that?
Instead of a multiple choice guess, they asked the model for a two-way confidence score.
Okay.
They take the raw probability the model assigns to the word correct and divide it by the combined probability of correct and incorrect. It isolates the model's absolute certainty. And they apply a punishingly strict threshold to this score, specifically 0.997.
Wait, 99.7%?
Yes.
So it's the difference between circling C on a test versus the teacher asking you, would you bet your life savings that C is correct?
That is exactly the difference.
The model has to be 99.7% certain the draft is flawless before it accepts it. If it has even a shadow of a doubt, it flags it as incorrect.
Right.
But if we set the threshold that high, doesn't that create a new problem?
What do you mean?
Aren't we just going to throw away perfectly good drafts just because the model was only, say, 98% sure?
You would think so, but that leads to their third and highly counterintuitive observation.
Which is?
Aggressive error catching does not waste good drafts.
Why not? If the threshold is 0.997, shouldn't it be rejecting almost everything out of paranoia?
Because of how the confidence margin distributes right and wrong drafts. The paper demonstrates that when a draft is genuinely correct, the target model's confidence score naturally clusters extremely close to 1.0. Yeah, it is overwhelmingly certain when something is right. But when a draft has an error, even a subtle one, the confidence score drops precipitously.
Oh, so it's not a gradual slope.
No, the separation between the two is incredibly clean. Raising the threshold to 0.997 captures all the subtle hallucinations and logical errors without accidentally misclassifying the actually correct drafts.
Okay, so the theory holds up. We have a highly confident judge, we can check multiple semantic chunks in parallel using the attention mask, and we aren't wasting good drafts.
Right.
But I want to see this operating in the wild. And there was one specific test in the paper's case studies that made this entire framework click for me.
I think I know the one.
The word problem about Kenny's Pokemon cards.
Yes, it perfectly illustrates the transition of control between the two models.
Yeah, let's walk through it. So they fed the system a multi-step math problem.
Right.
Kenny wants to buy an amusement park ticket that costs $100. He decides to sell his Pokemon cards for $1.50 each. He keeps 1/3 of his collection, sells the other 2/3, buys the ticket, and ends up with $50 left over in spending cash.
Right. And the prompt asks, how many cards did Kenny start with?
Right. So the fast, lightweight draft model takes the first pass. It writes out the whole solution instantly.
And it starts off brilliantly.
It does. It sets up the algebra, noting that the money from selling the cards is $1.50 times 2/3 x, which simplifies neatly to just x.
Sound logic.
It deduces that Kenny needs $150 total, the $100 ticket plus the $50 in cash. But in the final sentence, the draft model fumbles the conclusion.
Right, the hallucination.
It outputs x equals 50, therefore Kenny started with 50 cards, which is mathematically wrong because we just established he needs $150.
Exactly. Now, in a classical token-level system, the target model likely would have rejected the draft during the very first algebraic step.
Just for phrasing the equation differently.
Yes, just for a stylistic difference. In a sequential semantic system, it would have paused generation to verify the setup, paused again to verify the simplification, and so on.
The stop-and-go loop.
But Parse takes that completed draft, complete with the final error, and processes it in one forward pass.
The target model looks at it through the custom attention mask, evaluating every step simultaneously.
And it precisely isolates the failure point. It accepts the algebraic setup. It accepts the simplification to x. It accepts the deduction that Kenny needs $150.
Based off of good stuff.
It accepts all of that reasoning and places its incorrect flag squarely on the final chunk, x equals 50.
Oh, wow.
It preserves 80% of the draft model's accurate work, and the large target model seamlessly takes over from that exact boundary.
Without retyping the first 80%.
Exactly. It recalculates and outputs x equals 150. Therefore, Kenny started with 150 Pokemon cards.
It rescues the vast majority of the computational work and just corrects the typo at the finish line. When you scale that efficiency up across millions of queries, what kind of hard speedups did the researchers actually record?
The benchmarks are substantial. Testing on a massive target model, Qwen 3235B, across complex math, coding, and general reasoning tasks, Parse achieved a 1.25x to 4.3x speedup compared to running that large model natively.
Wait, up to 4 times faster for the exact same quality of reasoning?
Yes, and crucially, Parse is orthogonal to existing token-level methods.
Meaning you can mix them?
Exactly. You don't have to choose one over the other. You can use a token-level drafting accelerator, like Eagle E3, to make the small model type even faster.
Okay.
And then use Parse to handle the semantic verification of that text. When they stacked Parse with Eagle 3, the speedups compounded, reaching up to 4.5 times faster inference.
Because they're attacking 2 completely different bottlenecks in the pipeline.
Exactly. But there's one final detail in the results that points to how versatile this will be in the real world.
Oh, what's that?
It's called cross-family generalization.
Right, I noticed that in the tables. They were mixing and matching completely different brands of AI models, weren't they?
They were. They ran Parse using a target model from one architectural family, GLM 4.7, and paired it with a draft model from a completely different family, Qwen 3.5.
So different companies, basically.
Yeah. These are models with totally different pre-training data, different tokenizers, different chat templates.
They essentially speak different mathematical dialects.
And the GLM boss was still perfectly capable of grading the Qwen assistant's homework.
Flawlessly.
Flawlessly. It proved that this confidence-based error identification, the ability to evaluate whether a logical step is valid, is a universal, generalized property of large language models.
It isn't just a quirk of models that share the same training run.
No, you can theoretically pair up almost any extremely fast, specialized small model with any massive, highly intelligent target model and achieve these parallel speed benefits.
Which brings us back to why this matters to you, whether you're coding a website or just trying to get an AI to organize your weekly schedule.
Absolutely.
We started by highlighting the immense computational weight and latency of running massive models. What Parse demonstrates is that the future of fast, responsive AI isn't necessarily about forcing gigantic models to generate text faster.
No.
It's about teaching them to be master editors. It's about efficiently reusing the accurate work of smaller, cheaper models and only deploying the expensive, heavy reasoning power when it is strictly necessary to correct a mistake.
Right.
And for you, that architecture translates directly into faster, significantly cheaper, and far more accessible AI tools that don't compromise on the deep reasoning you need.
And if we abstract this out, it leaves us with a fascinating implication about the future economy of IT is.
Oh, how so?
Well, we established through the Parse experiments that for AI, judging is fundamentally easier than answering. Spotting a logical flaw takes less capability than creating flawless logic from scratch.
Right, the restaurant review concept.
Exactly. So if AI systems can eventually generate thousands of fully realized drafts, code bases, or business strategies in a fraction of a second.
Which they will.
Right. If the cost of generation falls effectively to zero, then the bottleneck is no longer creation.
The bottleneck becomes verification.
In a world of infinite, instantaneous idea generation, human value might shift entirely away from being the creators and move almost exclusively to being the curators.
We become the ultimate critique AI.
Yes, our only job is to sit in judgment of an endless stream of machine-generated possibilities, guiding them toward what is actually useful.
We stop being the authors and become the editors of an infinite idea machine.
Exactly.
Well, definitely something to think about the next time you are staring at a blinking cursor, waiting for the machine to reply.